previous lectures, we have discussed the introductory topics on machine learning, and then we came to a discussion of artificial neuron. Especially, we have talked about perceptron, which is a particular type of artificial neuron that is used for binary classification when the data are linearly separable. Now we will take that artificial neuron and we will try to make something that we have talked about so far, that is artificial neural network. That means we will take a bunch of artificial neuron, put them together and see what it can do for us. So in this lecture, we'll see that structurally how an artificial neural network will look like, and then we'll look into an example of artificial neural network. We started our discussion, if you remember, that generalizing certain structures that we have already used in other topics. For example, simple linear regression, so to say. Here the input is 1 and x, then 1 is multiplied with w0, x is multiplied with w1. We sum them up together, we get this z, which is w0 plus w1x. I pass this g through an activation function, this phi, and in this case phi z doesn't do anything, it just spits out the same function. I get my output, that is y hat. This is simple linear regression. In case of a perceptron, we are not interested about such regression, although perceptron is very similar in every other aspect with regression, but here the activation function is different. We see that the activation function gives a binary output. Here again, just like regression, the 1 and x, they come as input. They are multiplied with w0 and w1 respectively. We sum it to get z, which is again w0 plus w1x. We pass it through the activation function, and depending upon the value of this particular z, activation function will give me either 1 or 0 and nothing else. So eventually the data that is coming in, that is my x, which is a real number, the output will be an integer 1 or 0. That means I'll classify the data in one of these two groups, 1 and 0. Now these two structures, if you look into it, they are similar. They are taking some data, multiplying with some weight and bias, summing them up, passing through an activation function, and that is the general structure of artificial neuron, and we have discussed this structure before. When we combine such general structure in a complex network, what we make is the artificial neural network. Why do we call it neural network? Because it resembles the nervous system of animals, including human. Our nervous system has nerve cells like this. These are actual biological neurons. These nerve cells take impulses or signals through these terminals. Then this cell will pass this signal through this action. This action will again break in multiple terminals, and there will be a terminal to terminal connection with another neuron. Here, this is how the nervous system will transmit the signal. The connection here, as you can see, is not a hard connection. In fact, there is a gap here, so they are not physically connected like an electrical circuit. What happens that there are neurotransmitters which transmit in bursts. So these neuron to neuron connections are via electrochemical bursts. So electrical impulses, sometimes they will pass through it. It is not passing continuously. Now this structure, even though it looks very simple, that it is taking some impulse and then doing some processing over here, passing through another, and it is not passing continuously, it is passing through burst. There is very complex network of it within our body. Individual neuron may look very simple, they are doing a simple job here, but then when we connect them together, we can have very complex tasks performed, such as all human action that we are doing when we are walking, running, dancing, this kind of physical movement. Always we have multiple inputs are going through the neuron to our brain, and then we are having those physical movements. So it's a very complex problem, complex motion. But the units which are performing this complex signal, giving or taking of this complex signal, processing of these complex signals, those units themselves are actually very simple. And this is the inspiration behind artificial neural network. These are bio-inspired model of computation. We try to make a model of this neuron, which you have seen in our artificial neuron that we have discussed. And then we have a functional abstraction of biological neural structure. The way this system works, we have abstracted this in some way. We have simplified it. We have put it into mathematical model. And then we are using it to solve very complex problems. As we have already mentioned, the individual neuron, task-wise, they are simple, but collectively, they will solve complex problems like regression, classification, or recognizing very complex patterns. A typical neural network, which we call a feed-forward neural network, which is the simplest kind of neural network, will look somewhat like this. We have an input or something we call input layer, because there are several neurons at the input. Then there is an output layer here. So we have this output layer. Between input and output, there are also layers. And those layers, we call them hidden layers, because they are neither input nor output. They are doing something in between. This kind of neural network, we are calling them feed forward, because here signal goes from input to output in one direction. Signal will not come back from output to input. Although there are other type of neural networks, such as the recurrent neural network, where signal can flow backward, but here it will not be like that. This is the simplest structure of neural network. These hidden layers, what you see here, they all have these nodes, but over and above, they can have bias. So that means one additional input of 1, they can come here, those bias nodes. So they can give an additional input of 1, because that's what the bias do. Here also we can have a bias node that will give us 1. Each of these nodes individually, they are actually artificial neurons. And the data they are giving, all this data, you can see that if you look at each of these nodes, for instance, this node, it is taking up 1, 2, 3, 4 data. And if there is a bias, it will take 1 as well. So even without any bias, it is taking this 4 different data. Then it will multiply this 4 different data with an weight vector W. It will apply an activation function over that, and it will then pass this, whatever the output is, to the next one. And this is how it will go. In fact, each of these nodes, they can have different type of activation functions. They can have different weights. Each line is connected to one weight, and in general, they are different. Matching the output and input, we can have an optimized version of the weight vector. And that is what we do when we train artificial neural network. We need training data on data where inputs and outputs are known to us. We need that kind of data. We take that data and use the input here. We get some output from the neural net. Because we know the actual output, then the neural net output minus actual output, that will give us what is the error in our neural net. And eventually during training, we'll try to reduce the error, minimize the error as much as possible by changing this weight vector in every layer. Every layer will have weight vector now. Earlier we were talking about an individual neuron only, so it has very few weight vector, but here every layer will have a weight vector, and we'll try to get the optimum values of weight vector that will make this error to be minimum. Once I hit the optimum value of the weight vector, the training of neural network is done, and at that point I can deploy neural network to predict the output of unseen data, or what we call test data, the data for which we don't know the output. Once the training is done, that kind of data with unknown output data, I can put them as input and I can get the output, so it can now solve real problem. So neural network by itself is not giving us a mathematical model. It is only training all the weights and biases based on the training data, and then we are using unseen data and we are getting our prediction from neural network. This particular neural network which we are showing here, it has only 2 hidden layers and very few nodes here, very few neurons here. But in reality, the neural network may have large number of hidden layers and large number of nodes. When we have large number of hidden layers, that is the problem we call deep neural network. And how do you deploy deep neural network? How do you find the weight vector in deep neural network? That is a complex problem in machine learning. What we call a particular branch of machine learning tackles that problem, and we call that deep learning. So we are not going into those details. I'm just talking about here a very simple network with very few nodes, and we'll look into an example of such network. But before you go to the example, let us first see that what are the different kinds of activation function that we can have. Neural network, depending upon the problem at hand, can use a lot of different activation functions. So let us see some of them. We have many options for activation functions. Some of the popular activation functions, we are listing it here. One is the sigmoid or logistic function. Sigmoid function is over here. It goes from, for any input x that we give, it will go from 0 to 1 smoothly. 0 to 1 can go in jump. That is a jump condition that we have seen in perceptron, but this is not a jump condition. Jump condition is sometimes difficult to handle mathematically because we cannot differentiate jump condition. But here, sigmoid function, you see that it is closely mimicking the jump condition, but it is not exactly the jump condition. It is smoothly varying from 0 to 1, and it will never go below 0. It will never go above 1. You can see it from here. If this z takes a very large value, then e to the power minus z will be very small, closer and closer to 0. Then it will hit 1. So z tends to infinity. The value of this sigmoid will be 1. On the other hand, is z takes a negative value, very large. Then e to the power minus z will take very large value. That means 1 by very large value. So as z tends to negative infinity, this sigmoid will go to 1 by very large value. That means it will go towards 0. So always this function stays between 0 and 1. Sometimes we want some function to go between 1 and minus 1. And at that point, these tan hyperbolic type functions are very useful. Here, this is minus 1 as z goes to very large negative value. When it is z is very large negative, then e to the power z will be very small. We can neglect it. This we can neglect. And here you can see that if we neglect the first part, this minus e to the power minus z plus e to the power minus z, it gives minus 1. So it will hit minus 1 as z goes large in negative direction. On the other hand, if z goes large in the positive direction, then this e to the power minus z will be very small and we can drop them. If I drop this e to the power minus z, e to the power minus z, then it becomes e to the power z by e to the power z. That means it becomes 1. So hyperbolic tangent goes between negative 1 to 1. It goes smoothly, but then this smoothness can be controlled and it can come very close to a jump condition, but it is not exactly jump condition. It is smooth. Therefore, we can take a derivative of it. That becomes useful when we apply this gradient-based optimization algorithm in neural network. So these are one class of activation functions. There are other classes as well. Another important class is this rectified linear unit activation function. This rectified linear unit activation function is this: in positive direction, it will give linear; in negative direction, it will give 0. So which means that this phi of z is equal to z if the z is greater than 0. In positive direction, it's simply linear, making 45-degree angle, it not changing anything, but it is taking away the negative part and setting it to be 0. So here it is 0, and for negative x it is 0. This is the blue line, that is our ReLU. We can write it as 1 by 2, that is modulus of z by z. So when z is positive, then modulus of z is equal to z. So z plus d is twice z divided by 2. So this would be z. When it comes negative, then modulus of z and this negative, so this z less than 0, then modulus of z plus z will be 0, because this is negative and this is positive, same value. So it will be 0. So you will get 0 here. So negative part is 0, positive part no change. This is the linear function in positive part. So we call this rectified linear unit. Rectified linear unit, once again, at the origin you cannot differentiate it. There is a sharp variation here. So we sometimes use this soft plus, which will be log of 1 plus e to the power z. If you plot it, then e to the power z, when it goes negative to a large value, e to the power z will go to 0. It will come log of 1, that will be 0. So in negative direction, if you take this z, so that means if z tends to negative infinity, this phi will tends to 0. So that is what is happening. On the positive side, it will go very close to this ReLU function, because 1 will not, when z is positive direction in z, value of z is high, then e to the power z will be very large compared to 1. So 1 plus e to the power z will be z tends to infinity, then 1 plus e to the power z will be more or less equal to e to the power z, and log of e to the power z will be z. So in the positive direction, it will take, when the z is high, it will take simply linear. So it's very much like ReLU function, but near the origin it is different. It is smooth, so we can differentiate it and apply the optimization algorithms here. And finally, we have already seen two particular activation function. One is this binary step function, which we have used in perceptron, which will give us 1 or 0 output. When this z is greater than or equal to 0, it will give us 1, otherwise it will give us 0. And the identity or linear function, this is also called linear. In linear function, I have the z, whatever it comes, I just keep it like this. So it becomes linear, both in positive direction and in negative direction. Rectified linear is same as this linear in positive direction. In negative direction, it doesn't take negative. The negative part, it makes it 0. But the linear function, it takes whatever it is. So both positive and negative, it will take. ReLU will kill the negative part. So now, based on this discussion, let us just see one particular small neural network in action. So here you see an example of a neural network, very simple case of neural network. And you can play around with it. This is in playground.tensorflow.org. TensorFlow is a software that we use in neural network as well as in deep learning. In this neural network, this is my input layer. Then I have a hidden layer here. I have a hidden layer here. And they give us an output. The output is shown here. I can select as an input from here. Here are my inputs, and I can select some of the parameters. For example, I am taking here the tan hyperbolic activation function. There are other activation functions. I have ReLU here, tan hyperbolic, sigmoid, all are here. Then we have regularization. I didn't talk about regularization, so let's keep it at none. Learning rate, there is a fixed value here. Let us not change it. And problem type is classification. We can also do regression here. But let's see what it does in classification. We have a data set like this. You can see the data set here. And this data set has two types of dots. And these dots, they have this -1 and 1. You can see here that the color is showing -1 and 1. So -1 and 1. So this is a binary classification problem. This -1, 1, they don't mean anything. It could be as well be 0 and 1. They don't mean anything. Now you remember that in perceptron, we are having this decision boundary. So for example, if I take this kind of a data set, there can be a linear decision boundary between them. And then it becomes very easy, very simple. So let us try this data set and see what happens. So I am running the neural net. You can see that neural net is quickly coming to a convergence, that is giving me a line like this. That is my decision boundary here. I can reduce the number of neurons and let us run it once again. You can see that it doesn't make any difference because this is linearly separable. Just one neuron will be good enough. So it doesn't make any difference. I can take out one hidden layer, run it once again. You see that it doesn't make any difference. It's very simple. I can take out both the hidden layers. It doesn't make any difference because it only requires one neuron and nothing else. Right now, this is a simple perceptron, what we have discussed, and nothing else. However, as we go to complex data like this, then we need hidden layers. And a simple perceptron will not work. So let us see if we run this with the same activation 10H function. And we run this. You see that it is beautifully, it has created a decision boundary. This is one decision boundary. So inside there is one type of data, outside another type of data. Very quickly it has created the decision boundary. If I change the activation function, so let us say ReLU, it is once again it has created the decision boundary, but now it is not curved. All are multiple straight lines it has created. Because ReLU gives straight line as output, that you remember. We can take sigmoid and let us see what it does in sigmoid. Sigmoid is taking more time, but it is going quite all right. You can see that it has now classified properly. If I take linear, it will be difficult to have a linear classification here because this data is not linearly separable. So it is not going anywhere. You can see that here the error is not coming down at all. So linear is not doing very well here. So we have seen that 10H actually works best here. If I reduce the number of neurons to 3, does it work? It still works very well. We reduce the number of neurons to 2. Now you see that there is a problem here. 2 is not good enough to give a good boundary. So we need 3 at least. 4 may be overkill, but 3 minimum is needed. If we reduce the number of hidden layers, it is still good enough. We don't need that many hidden layers. We can have one hidden layer. We can increase one neuron in my hidden layer and you can see that it is good enough. You can change it to ReLU. It is not good enough. It is asking for another hidden layer. So you can see that with ReLU, we need another hidden layer. Here, of course, in this simple data set, we can have linear and it should work here. You can see that the linear works here. Linear because this is linearly separable. So linear activation will work here. We have already seen that this will work here. One hidden layer will work here. We can remove this and it will work here with no problem. So you can see that because this is a linearly separable data, it's very simple data. It is working now just like a perceptron. So there is no problem here. Go back to another complex data set here. You can see that here data set is more complex. If I try this kind of model, this model will not be good enough. So let's try here. See that it is not going anywhere. The error is not correcting so much. If I change it from linear to tan H, still it is not doing anything better. So we add some neuron here. Yeah, now you can see that it is doing much better now. It has now segregated the data set very well. Near the boundary there is some problem, but it's pretty good. Let us add one more layer. Now you can see that the segregation is even better. Can add one more layer. It doesn't make any difference. We can change here the activation. This is the ReLU activation. ReLU activation gives a zigzag type pattern, this linear type pattern here, but it is doing the job pretty good. Sigmoid should also do the job okay. It is taking more time than tan H, but it is doing pretty good. You can see the error is coming down. What about linear? Well, linear has a problem. Error is not coming down. It's a too complex data set for linear. So you can see that the tan H is probably the quickest to give us good result. Similarly, we can go for more complex data set like this one. This is a more complex data set. You see that 1 and -1, they are connected spirally. So it's a very difficult data set to classify. So let us see how the neural net does its job. We are going with this tan H with 2 hidden layers. And the net is still converging. You can see that it is converging. But it has somewhat now stalled and it is not doing much. We can check that with more hidden layers. Can we do something? You can see that this is not very easy to classify this kind of a data set. We have to try with different kind of trials that where it can have the best result. We have few more parameters here that we can change. Here we have ratio between training and test data. So some of this data are being used for training and some of this data are being used for test. Here the ratio by default is 50-50, but you can have this training to test like 70% training and 30% you will test. That is possible. Here training loss and test loss, the loss function is training and test. They are showing both are pretty much same here because it is segregated so perfectly that it has no problem. But training and test will be very different if you have a complex data set like this. So you can see that this test loss is very high here. Now the test loss is coming down somewhat, but even so the training loss and test losses are not same because all this data you can see here, this blue data are falling within this yellow zone. So all these losses will continue to come and there is oscillation. It cannot optimize any further. So these are complex data set and it requires complex pattern that you can play around here and try to see that how you can generate a proper neural network structures to classify such data. So this is where you can get an idea that how to build your own neural net. But before even you build your neural net, you can try this software by your own and see that how it actually works, get a physical feeling of this. The software is open source. It can be downloaded and installed in your own computer as well. And there you can test it graphically, that how does it work for a practical data set. Let us now summarize what we have learned so far. We have talked about artificial neural network. This is a bio-inspired computing model. This can do regression, which is quite obvious from our discussion. It can't do classification. We have seen that before in our discussion of perceptron and right now in a full-fledged neural network. And it can recognize patterns, which we have of course not discussed here. This is a part of unsupervised learning, which we are not discussing. But in a complex data set, neural network can bring pattern out of the complex data set. This is a data-driven technique. This is a tool in machine learning. So neural network is useful only when you have a lot of data, you don't know what to do with so much of data. In many typical problems that we deal with numerical methods, they are not data-driven. There is a model, we solve the model. And in such problem, neural network may not be of much use. But when you have lots of data and you want to get a prediction out of those data, you don't have a clear model, or you have a clear model, but you don't know how to solve the model. In such cases, the neural network will be very useful. As I have mentioned, that neural network is a bio-inspired model, and bio-inspired models are very common in numerical computation. As your exercise, you look at literature and you name 2 more bio-inspired techniques that we use in computing, especially problems related to engineering. That's all for this lecture. Thank you, and I'll see you in next class.